Hey everyone, in this video we're going to discuss some applications of override select control and feedback control loops, and we're going to do this mostly by going through a few examples. Alright, so first we're going to discuss a few applications of select control. So for the first example we'll go through and discuss how select control works for controlling the bottoms composition in a distillation column. So if we think about the general feedback control loop for this process, we want to control the bottoms composition, so we care about the composition that's coming out of the distillation column. So because we care about that, we measure it. So this is going to be our control variable, which is the composition. We have our primary controller is going to be this composition controller, so we'll have a set point for the composition controller. So if we think about how this is going to work in feedback only, so if we have a feedback only controller, the composition controller would just change this valve right here. Okay, but we're not doing just feedback control. We also have things set up like the composition controller is cascaded to the flow of steam. So we have a cascade control on the steam. So we measure the steam flow. We have a flow controller. And so the composition controller is now cascaded to the flow of steam, which controls the valve position on the steam flow. So this cascade system accounts for disturbances in the steam pressure that might affect the flow without anything changing in the feedback control loop. Okay, so when the system is operating properly as it's intended, what can happen is a disturbance to the system. So, for example, maybe the main disturbance is going to be the feed flow to the column. So the main feed to the column, the flow to the column can increase or decrease or change. And that's going to affect the amount of heating required in order to achieve the composition or the desired composition coming out in the bottoms. In some cases, once this feed becomes very high, the amount of the steam can no longer do enough heating to keep the composition where it needs to be. Okay, so in the case where this feed flow greatly increases, at some point the valve position on the steam fully opens. So if this valve position on the steam fully opens, the select controller that we now incorporate in here, so now we're going to add a select controller into the system, and the select controller is going to take a measurement of this steam. So what the select controller is going to do is the select controller is going to measure the flow of the steam, and if this is maxed out, now the select controller, rather than changing the flow control to the steam, which it can no longer change, it's going to keep that maxed out, and now the select control is going to go to a flow controller on the feed rate, and it's going to control the flow of feed to the system. So what happens is that under normal operation, when the steam flow is below the maximum flow, the select controller controls the composition based on the heating duty to the boiler at the bottom of the distillation column. Once this flow is maxed out, okay, so for example, the reason why select control is needed is because this feed disturbance is, in some cases, it might be too high such that the steam can no longer compensate for those changes. So when this is maxed out, the select controller switches to control the flow of steam entering the column. So what a pure select controller do, it'll change between your primary manipulated variable and a secondary manipulated variable. And the secondary manipulated variable is set up on the disturbance to the system. So in most cases, we want to have the maximum, we want to have all of the feed that we can take into the column come in, and we control it based on the steam. In some cases, this might be too high, so we need to back off when this is maxed out. And this will allow the system to operate as we need it to. Okay, we're going to look at another example now, and so we're going to go ahead and set this up. And so for this example, it's a fairly simple example. We're controlling the level in the tank. So we have a flow controller to control for the level in the tank. So this is our primary control objective, using the flow coming out of the tank. Okay, in this case, the main disturbance is the flow in. So this is our main disturbance. So we can think about some cases where if we're trying to control the level and this valve is maxed open, so if this valve is fully open and the tank is still filling up, so this is fully open and the tank is still filling up, we need to be able to accommodate that somehow. So what I want you to do is pause the video and think about how you would incorporate a select control on the system to prevent or to control the level in the event that this valve is wide open. All right, so let's think about how we're going to do that. So what we did before is we had a select control. So what I'm going to do here is I'm going to do something first. I'm going to add a cascade loop to the flow control coming out, just because. So we have a flow controller now in our primary control loop. Our primary control objective is the control in the level. So the level controller sends a remote set point to the flow controller. It takes the measurement of the flow and we open or close this valve as needed. Okay, so now we have this cascaded. So what this is going to do, what this cascade system is going to do, is it's going to really account for changes in pressure downstream from this valve to keep this at the target flow. So we also, now we want to have a select controller that says if this valve is fully open, we want to control for something else. So there's really only one other thing we can control for in this. And like we said in the previous example, we put a manipulated variable on the main disturbance. So what I'm going to do here is I'll put a control valve on the flow coming in. Okay, and also, erase this. Okay, so we'll put a control valve here. I'm also going to measure the flow, and I'll put a flow controller on this system. Okay, so now in the event that this valve is fully open, we want to control the flow coming in here. So we'll back off on this flow to keep the level where it needs to be. So I'm just going to draw a select controller right here. Okay, and so what we said in the previous case is now our primary control objective, we need to go through the select controller. So this controller, the primary control objective, goes to the select controller. And then the select controller under normal operation is going to send the remote set point from the primary control objective to the flow controller coming out. But what this select controller needs is it's going to need a measurement of the flow. So the select controller takes a measurement of this flow, and so in the case that this flow is not maxed out or this valve is not saturated, then the select controller will control the flow using the primary manipulated variable. When this is maxed out now, which it will know based on the flow signal, the select controller will then control for the flow coming in, and it'll have this control, so it'll start closing this valve. So under normal operation, this valve will be fully open, but when this valve is maxed out, the select controller will now start closing this valve to keep the level at the target level. So that's how select control will work in the level in the tank. All right, let's look at another example. We'll use temperature control in a heat exchanger, and we'll start to see that a lot of these examples become pretty similar. So what I want you to do, let's look at this and set it up in feedback control only. So what we're going to do in this case is we have our primary control objective for the heat exchanger is the temperature of the product stream coming out. So we have a process stream that's being heated by steam. So steam enters, condensate comes out. And we're going to heat the process fluid using steam. So what I'm going to put on here is, we can put a pressure controller, flow controller, temperature. I'm going to just call this a pressure controller. We'll put a pressure controller on the steam. So what we need to do is we need to measure the steam pressure. Okay, normal feedback control, we're measuring the temperature and we're going to cascade this to the pressure controller. Okay, so what happens if the steam is fully open, but the temperature coming out is too low? We need a select controller to adjust the system to keep the temperature coming out, temperature in this product stream at the specified system. So pause the video, think about how you would set that up, go ahead and attempt to draw the system, and then we'll discuss it in just a minute. All right, you got it? So this is what we're going to do. Now, instead of our primary control objective is now going to go to a select controller. Okay, so that's what I'm going to do here. I'm just going to have this go to the select controller, and the select controller goes to this because we need the system to operate as it's intended under normal operation conditions. So what's going to change in the system to cause the temperature coming out to be too low is if this feed flow gets too high. So if this feed flow gets too high, right, we're going to need to back off on the feed flow. So in order to do this, we'll put a valve on the feed. Okay, we need to measure the feed flow. I'll put a flow controller on here also. So we have the flow controller is changing this valve. Okay, so the select controller is now going to, what would it do? It's going to measure this pressure, or it's going to measure this steam flow, or it's going to measure something associated with the steam. Okay, so if this steam pressure is maxed out or the steam flow is maxed out, we'll take the measurement of that we'll take the measurement of our primary manipulated variable. So the steam is our primary manipulated variable. We take that measurement to the select controller, and when this is maxed out, we can no longer change this valve. Then the select controller is going to then instead control for this. So under normal operating conditions, again, this valve would be wide open, and once this steam flow is maxed out and the temperature is still too low, we'll back off on the feed flow to the system, and we'll keep the outlet temperature at the necessary temperature. All right, so for this final example, it's not really an example. I want you to come up with an example. So think about the systems that we looked at and come up with an example for using select control to improve the performance of a feedback control loop. So the way you can think about this is when the feedback system is behaving properly. So when the system is behaving properly and the final control element is fully open or closed, the select control needs to know that. So you need to measure something around the final control element, which is the main manipulated variable. And then the select controller is going to take that measurement, figure out that it's maxed open or maxed closed, and then decide to use a different control valve. So for example, we set a valve on the disturbance to control for the process. And you can do this by reviewing what we did in different examples. So I want you to think about this, work on it. This is something that you will need to do for the next exam, or you'll see something like it. All right, so select control can also be used in a variety of different ways. We can have select controllers on a temperature. So here's an example where we have various measurements of a temperature, and this would be a packed bed reactor. So in a packed bed reactor, it's like a pipe, and this pipe is full of catalyst. In catalyst can get hot in different areas. So what this will do is measure the temperature of the catalyst in various areas and then use the maximum temperature. So we have for the temperature of the system, we have a T specified. So we take the maximum temperature, and the controller will adjust the flow of the reactants. So we have the flow of reactants into the system to keep the temperature where we want it to be. So select control can be used in terms of temperature measurements in addition to control systems. All right, now let's look at another example of override select using the furnace tube temperature constraint control. And this is an example we looked at last time. This time we're going to go through and set it up with a system that you're a little familiar with. Okay, so let's first start by reviewing the process. So in this case, we're using a furnace. So here we have a furnace. And the furnace is heating up a process fluid that's traveling through the furnace. So we have a process fluid that goes through the furnace. And so we care about the temperature coming out. And so we have a temperature controller that's going to take the measurement of that temperature. We're going to have a specified temperature, and this is going to go to another process like maybe a separation or a reactor. And in feedback control mode, this system is going to adjust the flow of fuel that's going into the furnace. Now notice here that we have the fuel flow is set up in a cascade. So the temperature of the process fluid exiting the furnace is cascaded to the flow of fuel that's sent to the furnace. So the manipulated variable is going to be the flow of the fuel, and it's cascaded. So one thing you can do is think about what disturbance is this cascade loop going to accommodate for. Okay, these are things that we should know from previous lectures. Okay, so now we're going to have a constraint in the system. So one thing that can happen is that if the flow of fuel gets too high, these tubes, so the tubes that the process fluid flows through, can get too hot and can wear and degrade fairly quickly. So we want to have an override loop that prevents these from getting to a maximum temperature. Okay, so in order to incorporate an override loop, we need the same things that we need for a feedback control loop. So we need measurement of the system, and we need measurement of the tubes. We need a temperature controller. So again, we have a temperature controller. All right, so also what we need on here is we're going to need a specified value. So the specified value is going to be the temperature constraint or the safety constraint. And for this case right here, it'll be the maximum temperature. So Tmax is the maximum temperature. Okay, so when we have override select, we'll have another controller. So in here, we're going to put another controller. And this controller is going to select between the primary control objective, which is the temperature coming out, or the process constraint. Okay, so our limit is a maximum temperature. So sometimes people tend to think that if our limit's a maximum temperature, our select controller should be a low select, and that's not necessarily true, and we're going to see that in another example. Okay, what we need to think about in order to determine is this a low select or is this a high select is we'll look at the safety constraint or the override constraint loop. This loop, the objective of this loop is going to be to get this system to the safety constraint, right? So we want the maximum temperature loop its objective is to get the tubes to the safety limit or to the constraint. So we think about how that happens. So if this loop is going to get these to the maximum temperature, this controller is going to ask for a maximum flow. So essentially this controller, to get this to the constraint, is asking for a maximum flow of fuel. So a maximum flow of fuel. So because this signal is a maximum flow of fuel, to get this to the safety constraint, we have a low select signal because this is going to be the highest signal allowable to keep this below the set point. So under normal operating conditions, right, if the temperature specified, if this temperature is, under normal operating conditions, the controller is going to be adjusting the fuel rate. As long as this is below the limit, this loop will always be asking for a maximum signal, which is going to be a higher loop. So the safety constraint loop is trying to get this to the safety constraint. Now, once we start approaching the safety constraint, so when the temperature of these tubes gets hot and gets really close, and we're still below the amount that we're still below the specified temperature, once this starts asking for too high, so at some point this might ask for too high, when this temperature loop max out, this will be asking for the maximum flow. And if this flow becomes greater than the maximum flow, then this lower select controller is going to select the safety constraint loop. So that's how it picks up on the safety constraint loop and overrides the primary control objective of the system. All right, let's look at another example that's similar, but it's quite different. Okay, so we're going to have an override select loop or an override select control where the coolant which has coolant temperature constraint control. Okay, so in this system, we have a reactor that has a cooling water jacket, and the primary control objective is to keep the temperature of the product stream at a specified temperature, T specified. Okay, so I'm going to erase these lines for a minute. Okay, so in this case, we'll have the temperature controller in feedback mode only controlling the coolant flow. Okay, so if this coolant temperature gets too low, we need to change something to the system. So we need an override loop that's going to prevent this from getting too low. So in order to do that, we need to have a secondary control loop. So and we have another control loop where now we're measuring the temperature of the coolant water. Then we have a temperature controller for the coolant water. And in this case, we have a minimum. So we have a temperature that's a minimum. Okay, so now we're going to have a select controller incorporated into this loop. And the select controller is going to select between the primary control objective, which is the temperature of the product stream coming out, and the temperature of the coolant water going in. And so now, because this constraint is now minimum, All right, so remember, some people tend to think if the constraint is a minimum, then this should be a high select control, right? But that's going to be incorrect here, because we need to think about what is this controller doing in order to get this to be a minimum, right? So the safety constraint loop is objective is to get it to the minimum temperature, and by getting it to the minimum temperature, it prevents it from passing the minimum temperature or getting below the minimum temperature. So how would that work? So this controller, if this controller were going to change this valve position to get this to the minimum temperature, this would be a max flow, right? So because this is a max flow, right, and these specified values are flow or valve positions, this needs to be a low select controller. So the safety constraint is a minimum. The objective, or the set point, the remote set point that's being asked for by the safety constraint or the process constraint loop is a maximum. Therefore, we need a low select controller. Okay, so this is the theory that you can think about in order to decide between the low and select control. So if we're going to review select control, we have two control loops. We have one control loop for our primary control objective. We have a control loop for our secondary objective. We have both of those going to a select controller, and then that select controller changes the coolant water flow. We then have to determine, is it high select or low select? And we can determine whether it's high select or low select by looking at what is the signal coming from the safety constraint loop going to be in order to get the process to the safety constraint. And if that's a max flow, then we need a low select controller. Okay, so under normal operating conditions, when the temperature here is high enough to keep the reaction going, the cooling water flow is controlled by the main objective loop. And the secondary loop is trying to get this to the minimum, so this is trying to open the valve. So during normal operation, this right here is going to be a relatively high flow signal. Once the system, as the temperature increases and asks for a flow of cooling water, and at some point if the temperature of the cooling water gets too low, this controller, again, it's going to be saying the maximum flow of cooling water. This system right here, the product stream, might want this to be higher than the maximum flow that would quench the reactor. Therefore, the override loop is going to take over. Okay, so that's how override loop can be used to prevent the system from getting to certain constraints. There's one more subtle thing I want you to think about with this system. And you can think about this with various types of systems. We talked about this with respect to flow. So I like to put flow controllers here. So I'm going to put a flow controller here. Now in this case, where the signal is going to the control valve or going to the final control element or the manipulated variable are both flow signals. So we're comparing high versus low flow signals. This doesn't have to be set up in cascade. This could be set up where both signals are just going to the valve, and it could be an air pressure or it could be a valve position that's the signal. If we have now air to open or air to close, where maybe we decrease the signal in order to open the valve, or we increase the signal to close the valve, or vice versa, the design of this select controller can change. Okay, I'm not going to discuss that here, but I'm going to give you a hint. I want you to think about this same exact system right here, no cascade loop. How would this work? What type of controller would you have if you had air to open valve and your signal is air pressure? And what type of controller would you have if it's an air to close valve? Okay, a little bit of a hint for you. If it's air to open, again, high air pressure, high flow. Probably going to be set up the same way. If it's air to close, that means now low signal is high flow. So in that case, your constraint would now be a low signal. If it's a low signal, I think we might need a high select. Okay, make sure you can work through that. And if you have questions, feel free to ask. Okay, we're going to go again do another example. We looked at this one last time too. So here we want to control the composition in the distillation column. Again, another composition, controlling composition in distillation column. We're measuring the composition. Under normal feedback control, the composition controller would open or close the flow of steam to the boiler at the bottom of the column. This is set up in cascade. Again, we have the cascade loop to accommodate for variations in steam pressure at the bottom of the column. One thing we know can happen is that if the delta P across, if the vapor flow, so vapor flow is too high, the column can flood. We can get an indication of vapor flow by measuring the delta P across the column. Okay, so if the delta P across the column gets too high, we're going to need to back off on the amount of heating that's done at the bottom of the column to keep the vapor flow from being too high that causes it flooding. Okay, so what do we need to do? We first need to measure the delta P. So delta P, I'm going to actually call this delta P T, as in delta P sensor. So we have measuring the pressure difference across the column. We also need a DP controller. Okay, so in this case, it just combined them both together, but I'm going to separate them because I want to. So we need a DP max. So when the DP is max, the column can flood. So we want to keep this from happening. Okay, so like before, we add a select controller, and the select controller is going to select between the main objective, which is the composition, and it's going to select between the composition control loop. Okay, so I don't care that the safety constraint is a max. I want to think about what is this signal right here going to be to get this to the maximum delta P. High flow of steam or low flow? Well, high flow of steam is going to cause high vapor flow, which is going to cause high delta P. So this right here would be a high flow to get this to the safety constraint. Therefore, since this signal is a high flow, I want to select for the composition controller most of the time during normal operation. Therefore, I need a low select controller. During normal operation, this signal is relatively low. Again, it's the flow of steam is going to be relatively low compared to the maximum steam flow that would get us to our maximum delta P. Once this composition gets out of spec and the system starts asking for a higher and higher and higher flow of steam, delta P is going to increase. Eventually the delta P is going to reach this DP max. Once this delta P reaches this DP max, we will be at the maximum flow. If this composition controller is asking for a higher flow, then this composition or this delta P max loop takes over and controls for the flow of steam. So this then will be out of spec. So the composition will be out of spec for that period of time until the disturbance goes away and the system can recover. All right, we're going to go through a couple more examples that are a little bit more elaborate than the previous ones that have multiple loops, multiple objectives. Each loop, again, is going to be single input, single output. So again, each separate feedback control loop is going to have one measured primary control variable and one manipulative variable. Unless, of course, select control, which could change the manipulative variable if a valve saturates. Okay, so let's look at what we're going here. So we want to control the composition. So again, we want to control the composition of the distillate product with the reflux control valve. So the reflux control valve. We want to control the level with the distillate product flow. And then we have a max level constraint on the accumulator. Okay, so pause the video, set up these different loops, and we'll come back in just a minute. All right, you get it? Okay, let's step through this one by one. So we're going to control the composition, okay, the composition of the distillate product with the reflux. So that's our first objective. So here we're measuring the composition. I'll have a composition controller. So we have, again, a specified composition. That's our primary control objective. And this is going to control this valve. Okay, I'm just doing what's asked. It doesn't tell me to cascade, so I'm not going to put a cascade loop around here for now. Okay, so got that one. Composition with reflux control. The next thing, control the level with the distillate product flow. So I measure the level. I need a level controller, a specified level, control the flow. Again, I'm not cascading this because it doesn't ask me to. I can just open and close this valve to keep this level where it needs to be. And really, this probably doesn't need a cascade loop anyway. Okay, got that. Okay, so finally, I need a max level constraint in the accumulator. Okay, so if this accumulator is filling up all the way, that means if this continues to fill up, that means this valve is all the way open. So I can't override this loop because that's what I'm using to control the level. So I can only override this loop over here, the reflux. So if this fills up all the way, what I need to do is further open this valve in order to send more to the system. So what that means is that there's a minimum flow of this reflux to go back here to keep this from filling up. All right, so let's look at how to integrate that. So for the constraint loop, I need my own loop. So I need to measure it. I'm already measuring the level. I could put another level sensor on there if I wanted. I need a level controller. I need a set point, and this is going to be a max. So max level in here. And now this, we want to control this manipulated variable right here. So we'll have a select controller that's going to select between the constraint loop and the primary control objective, which is the composition. So now we need to decide, is this high select or low select? Okay, we do that by figuring out, so this control loop, the objective of the constraint loop is trying to get this to the constraint. So that would be a maximum level. In order to get this to the maximum level, the signal here, the constraint loop is saying close this valve. So this right here is going to be a minimum. Again, as long as the signal is flow, is going to be a minimum flow. If the primary control loop tries to close this valve too much, where it gets below the minimum signal, the level constraint loop will take over and open this valve to bring more back to help empty out the accumulator, and that'll keep this out of spec. Okay, so the constraint loop is telling the minimum amount of flow that can go to this valve to keep this below the maximum level. All right. So let's look at another example. And this example comes from the textbook. So this is problem 3.4.4. And we're going to go through and do a variety of loops related to this process. Okay, and we're going to go through them one at a time. Some of them are fairly straightforward. Some of them can get a little bit tough. Okay, so let's start at the beginning. So for this problem, it says, consider the schematic for an exothermic CSTR shown in this figure, in which heat is produced from the reactor is used to generate steam. So we want to draw the schematic for this process and include each of the following control features. So the first feature is the level in the steam drum is controlled by the makeup water. Okay, so we have level in the steam drum, so we need a level controller. We're controlling the level, so we have a specified level. The level in the steam drum is controlled by the makeup water. So I didn't say this already, but what you can do as we work through this problem is for each loop that I discuss, pause the video and set up the loop and then come back to visit me. Okay, but we already did the first loop. This one's pretty easy, so I think you got this one. Control the level by controlling the flow of makeup water. Okay, as the level decreases, we send more water into the system. Okay, the next part. The pressure of the steam drum is controlled by the valve on the steam line to the steam header. Again, so we have, in this loop, we measure the pressure. We have a pressure controller. So we're measuring the pressure. It's controlled by this valve right here, P specified. Okay, again, fairly straightforward. Make one measurement, open in valve. Okay, the temperature controller for the reactor is cascaded to the steam pressure control loop. Okay, so the temperature controller for the reactor, so here's the reactor temperature. The temperature of the reactor is the same as the temperature coming out in the product stream. The temperature of the reactor, we have a set point, T specified. is cascaded to the steam pressure control loop. So what cascaded to means is that this we talked about this last time, cascaded to means sends a remote set point to. So let's think about how this loop works a little bit. So we have the temperature controller is cascaded to the pressure, is cascaded to the steam pressure control loop. Okay, this isn't super straightforward in terms of how it works, but we can walk through it a little bit. And again, this is something that I'd think about, so you can pause the video. So as the temperature changes, it's going to change the remote set point to the pressure on here. And so it's going to either release more pressure, it's going to release steam, or it's going to hold the steam. As we release the steam, the level in the tank is going to change, which is going to bring water into the system, which is going to have a cooling effect. If we don't release the steam, we're not going to bring water into the system, which is everything, the temperature is going to continue to increase. Okay, so these two loops are related to each other, but they're still separate in terms of how they work. All right, moving forward. The level in the reactor is controlled by the product flow rate. So level in the reactor, we have level specified, product flow rate. Straightforward. Okay, a low level in the steam drum overrides the set point to the flow controller on the feed to the reactor and cuts back on the reactor feed. Okay, so what that means is that under normal operation, we have a specified feed to the system, F specified. Okay, it's important to recognize that. And for this part, we're saying a low level in the steam drum overrides the set point to the flow controller of the reactor. So we need a select controller right here. And the select controller is going to select between the specified flow and it's going to select between a low level in the steam drum. So I'm going to put my level controller right here. This is going to be my process. And so what's this going to be? So a low level. So Lmin coming from the steam drum. So we're measuring the steam drum. And this says is that a low level in the steam drum is going to back off on, or it's going to back off on the steam flow. Or sorry, the feed to the reactor. Okay, so in order for this to get this to a low level, how do we affect the feed to the system? So this is a little bit trickier to think about. So it's saying it's going to, if this gets too low, it's going to back off on the feed to the system. So that means essentially that this is going to be, should be a maximum flow. Okay, but let's think about how that's going to work. If this gets too low, so if this level gets too low, what that means is that the makeup water is coming in at a maximum rate. So this is coming in at a maximum rate. I can no longer fill up this level using the makeup water. Okay, so therefore this is doing too much heating. If the reactor is doing too much heating, that means this system, the feed to the reactor is too high. More feed, more reaction, more heating. So we need to back off on the feed. Okay, so in order to get this, in order to bring this level down, right, the safety constraint or the process constraint loop, the objective is to get it to the process constraint. So if I want to bring this level down, I want to have the maximum amount of heating that I can have because I'm producing more steam than makeup water I can have coming in, which means I need a max flow coming to the system. Therefore, this would be a low select controller. Okay. One's a little bit tricky, and this next one sort of the same. A high reactor temperature overrides the set point to the flow controller on the feed to the reactor and cuts back on the reactor feed. So I have something else that's going to cut back on this feed. So I'm going to use the same select controller, right? So that's going to select the minimum signal between between the specified flow, the flow that's going to control the water, or control the level in the steam drum, and now the product stream. So let's make sure that this can operate based on the same system, or else I'm going to have to add another controller. Okay, so a high reactor temperature overrides the set point. So high reactor temperature, I measure the temperature, I need a set point, so Tmax, this is my constraint loop. I'm taking the measurement of the temperature of the product stream, or of the reactor. So the temperature of the product is the same as the temperature of the reactor. Have a maximum temperature, and this override loop is going to cut back on the temperature here. So again, similar to what I discussed for the level in the system, this right here, to get this to a max temperature, I want to have a max flow. So this is going to tell me the max flow of reactants, because more reactant flow, more reaction, more heating, to get this to the max temperature. So this is going to be a max flow. So now we think about how all these works. We have a specified flow, we have a max flow due to the level in the steam drum, and then we have a max flow due to the temperature. So if this temperature gets too hot, if this temperature gets too hot, it's going to select between this temperature, it's going to take this loop over the specified loop. Right? And again, as this temperature gets too hot, it starts evaporating, creating steam at too high rate, the level starts to drop, makeup water can't accommodate for that. Level gets too low. Once this level gets too low, we know that we have too much heating going on. Therefore, this controller will cut back on the feed to the system, which will override either of these other loops. So both of these loops say the max possible flow for each loop. We have a specified flow. If these loops are operating okay and we're not at the maximums, or we're not at the process constraints, then we will use the specified flow to the system. Okay? I think we just have one more example, and then we'll talk about some computed manipulative variable. Okay, so this one's kind of interesting. Okay, in this one we're going to control the pressure in the distillation column using the level in the condenser. So here's our condenser. We have a level in the condenser. So as the level in the condenser decreases, we have more area available to condense the vapor. As the level increases, we do less condensing. So we can control the level. We can control the pressure by controlling the level of the distillation, or by controlling the level in the system. Okay, and that's controlled using this valve. So we want to control the pressure in the distillation column. So therefore, we need a pressure controller, P specified, we control the pressure in the column by changing this valve. Okay, simple enough. If the pressure gets too high, we'll open the valve and this will come down to relieve the pressure. If the pressure gets too low, we'll close this valve and raise the level such that it's not condensing as much vapor. Now we have a level constraint on the condenser. So I didn't say the level constraint. We could do max or min. Maybe pick one, maybe do both, and then come back to me. Okay, so we have a constraint. We need to measure the level. Let's call this L, what? Let's say max level. Right, why am I saying max level? Because if this fills up all the way, then we can no longer condense the vapor from the pressure, from the column. Okay, so if this is a max level, I need to, again, we need to control this valve. So I'm going to go ahead and put a select controller right here. So we decide between our pressure control loop and our level control loop. So level control loop. If in order to get this to the maximum level, I want to close this valve. Close valve. So this would be a minimum flow will get me to the maximum level. So since this is a minimum flow, this would be I select controller. Under normal operating conditions, this signal will be relatively low. As this starts to fill up all the way, that means the pressure in here is probably dropping. At some point, this flow will become too low, and then at this point, the signal here will become eventually drop down, become low, low, low. At some point, once this gets too low, the safety constraint loop will take over, and it will control based on that loop. Okay, there's other ways of operating this. We can cascade, we can do cascades, we can do all sorts of various things. Think about what are some other examples you might do with the system, or maybe look at some old tests. Okay, so the last thing I want to talk about in this video is a few examples of computed manipulative variable. Okay, so computed manipulative variable is when we have to calculate the manipulative variable in the controller instead of making a single measurement. So normal feedback control, you make a measurement, you compare that to a set point, and you take action on a control valve or another final control element. Computed manipulative variable often takes multiple measurements and does a calculation and adjusts a flow or a valve accordingly. So here's an example where we have computed manipulative variable on reboiler duty. So in this case, we have quench water. So what happens with the quench water is that if the quench water can have a temperature that changes, so we can have the flow, we're going to control the flow, so that's going to be our manipulative variable. The temperature of the quench water can change. So if the temperature of the quench water changes, the temperature of the quench water coming out is also going to change, and we know that the amount of heating is going to be based on the delta T. So we can't know what the temperature coming out is going to be, or it's not necessarily dependent on the temperature coming in. So we need, in order to get better control of the heating to the system, we need a measurement of both the temperatures coming out. So if we measure both of the temperatures coming out, we know the flow to the system required to give, we know the flow of the quench water required to give the necessary heating. Again, for my feedback control loop, I need a specified flow. I want to note that we could just measure the temperature. We could just measure the temperature and open the flow, or we could just have a composition controller adjust the flow to keep the composition where it needs to be. Right? We use the computed manipulative variable to achieve better control because the composition, we know how much heating is required to keep the composition where we need it to be. Right? That's different than we don't know what the temperature, we don't know the temperature required, we don't know the flow required to keep the composition where it needs to be. We know the heating required to keep that composition. Okay, so we set the flow based on measurements of the temperature difference and specified heating rates. And so we can do a simple balance around the flow. We can do a simple balance around the reboiler based on the quench water to determine the flow required to do the necessary cooling that we need for the system. So again, computed manipulative variable, it's going to improve the performance of the feedback control loop, which could be achieved by simply normal feedback controls. We could just have our composition controller adjust the flow of quench water in order to adjust the amount of heating to the column. It's just not going to be as efficient as if we can get a better measure of the actual heating rate. Here's a couple other examples. You can think about these. We'll discuss them a little bit. So here's an example where we have heat duty controller. So in the case where the disturbance is a low BTU fuel, if the flow rate of this fuel varies, it's going to affect the amount of heating in the furnace. So we'll have a natural gas backup stream. So if we have a high flow of this fuel, we might not need a lot of natural gas to do the heating. If this flow changes, we'll probably need to add a little bit of natural gas to get the amount of heating that we need. So the heating duty controller will take a measurement of this disturbance, the flow of low BTU fuel. It'll take the required amount of heating based on what the temperature we want coming out, and it'll adjust the flow of natural gas accordingly. And again, we could do this system. We could again, have T specified here. We could just change this valve, but by knowing what this flow is, we can essentially get a better measure of what this valve is before the system temperature changes too much. Okay, another system here is, again, we have internal reflux control on a column, where we know that the reflux rate is going to be related to the temperature coming out of the column, the temperature of the reflux stream. Our main set point is going to be the composition specified. This is our primary control objective. We can send the different measurements of the temperature to calculate what is the ideal flow required to keep this at the specified composition. All right, so that's going to be all for today. Practice some of these examples. Hope this helps with override select, and computed manipulative variable. And we'll see you next time.